So it's my great pleasure today to welcome Tilman Esslinger to the Collège de France as the first speaker of this seminar series. Tilman is, of course, a founding father of the field. You've seen at the beginning of the lecture today this seminal experiment in 2002 that demonstrated the superfluid mode transition with bosonic atoms. It's only one of a long series of pioneering experiments that Tilman has done in the field. He's been a professor at ETH since, I think, 2001, if my memory is correct. And he was previously at the Max Planck Garching, where this experiment was performed in particular. Since then, he has developed many different experimental works and achievements in his ETH lab, where I think he has currently 4 different experiments running. Is that correct? And he's been, of course, recognized by many awards. I'm not going to mention all of them, but several ERC senior grants and Philip Morris Awards and so on and so forth. And perhaps more directly, I have a wonderful memory of some great collaborations we had together, in particular having fun with good old thermoelectric effects in ultra-cold systems more than a decade ago. So Tilman, thank you so much for having accepted the invitation, and the floor is yours.
Thank you very much. This great pleasure to be here. Thank you for the invitation. Thank you for coming. So my talk will be at the interface of quantum simulation, quantum computing, and quantum simulation of devices in the second part. Maybe some of you had at some point, maybe on a Sunday afternoon or so, or maybe a whole week, thought about how could one build a quantum computer? What would I build if I wanted to build a quantum computer? So, and then you are, well, basically you have 2 possible routes to it. Either at the very early decision will be whether you take synthetic or natural qubits. So synthetic qubits I would call, well, like superconducting qubits, spin qubits, and so on, which is basically the solid state physics. Or natural qubits, there I would say atoms, ions, and photons. And now these different approaches, they have different challenges. The synthetic qubits, of course, to make them identical is a huge challenge, and most of the efforts go in there, and the connectivity. In, natural qubits, as a qubit, they are simple, but they also have their challenges. And there it is, in the end, instead of building identical, you have to precision them. That's a challenge. And you need to be able to transport them, in particularly if you want to achieve connectivity. And then there is a joint challenge that is a scaling. You want to scale up the system because otherwise your calculations are not so interesting. In this talk, I want to address the transporting and connectivity and scaling challenge. So if you think about transport, then if you zoom out, and then in the development of humanity, that we were able to transport classical cargo, not by just handing it over to the next person and so forth. When rollers were developed to, say, transport copper or whatever we needed, that was quite a development, and it's a long development and had several innovations until we are now at a very sophisticated level for wheels. I mean, modern cars, everything is perfect. Nowadays, we are at at a point where we need to think about transport of quantum cargo. And I do like a little bit the analogy, because there on the left-hand side, it also took some time. So now we have an exciting question, but it may also, well, for the final quantum computer, take some time. And what I will show you in this respect is an experiment where we produce singlet states of atoms, and we will use a topological pump to move them apart and bring them back. And not only that, but we do that in such a way, using swap gates, that they can pass through each other and back again. So that's what I will come to. And then there's a scaling challenge. To scale up, to have a lot of entangled particles, one might sometimes think, oh, yeah, this is difficult, or one could say, oh, this is trivial, but we are surrounded by entangled particles. I mean, if you think about molecules or everything around us, there are masses of paired electrons in the orbitals. So in principle, one could argue, I just take such a pair, and then, or many of them, I have plenty, and then I take them apart and do something with them and bring them back for readout. Yet, and then ideally I do it with many and connect them and bring them back for readout. So there are plenty of entangled pairs. However, it would need to be made in such a way, if you took the electrons out of the orbital, you need a process where you can put them back in snugly. So otherwise, you would introduce decoherence. And that's why we don't look at atoms, but at electrons, we'll look at atoms. So we will have singlet paired atoms, and we'll take those apart and bring them together. And for that, we let matter and light work together. And we just heard about the periodic potentials. And atoms, as you know, are polarizable. And using standing waves, we can create periodic potentials. And we can do that not only in one dimension, but also in 2 and 3 dimensions, imagine. And there's a bit then the role of light and matter change versus what we are usually used to. We are used to having coherent light and then some grating, and then we can see an interference pattern. Here is just the other way around. We create a grating with our light and put coherent matter here, for example, Bose condensate into this grating, and then we will see an interference pattern. Yet one has to be an important, so this illustrates a 2-dimensional situation. And we have thought here about this standing wave, the horizontal and the vertical, being independent. Yet there is a time phase. If they have the same frequency, there is a time phase between the two. And depending on the time phase, I might also create such a pattern. And what has been overlooked by us and our colleagues, that it is fairly easy to create both patterns and continuously move one with respect to the other. And that will be the key point for the robustness of our topological pump. To get many localized pairs, we start with a potassium-40 gas, fermionic gas, in different spin states, so that's then like spin up and spin down in the electrons. And then we expose them to standing laser waves in 3 dimensions. And with this, we end up having, if we have attractive interactions, we have singlet pairs sitting on the lattice sides. Not perfectly on every lattice side, but with a good fraction of the lattice side, maybe 50% or so, are filled with singlet pairs. And the physics of such a lattice, so these localized, these lattice sites are like our orbitals. The physics can be captured by the Hubbard model, and you can imagine, well, the atoms, it's all in the lowest band. The atoms here spin up and spin down, red and green. They hop from one side to the next side, and if they are both on the same side, they collisionally interact with each other. And here, the atomic physics is, well, that's one of the big strengths, that the interaction can be tuned using a so-called Feshbach resonance. So the collisional interaction can be tuned between attractive, non-interacting, and repulsively interacting. And how can we read out? So we can do all sorts of things, change interactions, change our light field, but how do we get the information out of the experiment? And an important technique that we use is actually certain precision spectroscopy, or in a way a radio frequency spectroscopy. And there we use that we have, in principle, even more Zeeman substates. And what we do is, if two atoms are on the same side and they interact, and now we can selectively transfer those where we have two into a third state, so that should come here, because of the interaction shifts the frequency with which we do the spectroscopy or the corresponding pulse. And then we can use simply a Stern-Gerlach effect to read them out, and then we can measure the number that we had on doubly occupied sites and those on single occupied sites. That's how we get a lot of information out of our system. And that's the view on the experiment. You see, it looks definitely like a quantum computer, but I will, of course, also give you the insider view, what it really looks like. So on the left-hand side, there is the vacuum system with its optic around. On the right-hand side, there are all the lasers, and the two tables are connected by optical fibers. And in the background, there's all the computer control to run this experiment. And most importantly is the team. Here I show you. And this team is led by Konrad Fiban and Jan Kiefer is another postdoc, and Sichia Su, the most senior PhD, now also postdoc on the experiment. So let's go back to our lattice with the singlet pairs sitting there. And as I told you, we are kind of a bit wizards in constructing these optical potentials. So we can also construct optical potentials where we have double wells. So we have a lattice of double wells, and where we can control these double wells. And now let's have a look at one of these double wells. We have a singlet pair created. We have one of these double wells. And now we go from attractive to repulsive interaction, which means just changing a magnetic field by a few Gauss, a homogeneous magnetic field. And then we shape our potential such we get a real double well. And that is the first step. So out of our localized attractively interacting singlet, we have produced a Heisenberg singlet in the sense that it is a correlated Bell state. I do not know which spin is on the left or on the right side, and the energies are such that the tunneling energy is small compared to the interaction energy. So I know I have filled both lattice sides, but I don't know which spin I have where. And to probe whether that's really the case, what we will then do is to move those apart. So there we have a little bit made out of a single orbital, kind of, we have them now in 2 orbitals, but now we want to move them apart. So, and that, taking the apart, there we use a topological pump. So what's the idea of the topological pump? It is a periodically driven system, and this allows you to move an insulating state or a localized state periodically by an exact amount during each period. And one way to implement this is to take a lattice with a short period. Let's see this here. A lattice with a short period and a lattice with a double period, and then you move this lattice with a double period with respect to the short period lattice. And this will periodically modulate the side offset. That's one of your parameters in the system, and the relative tunneling within the double well and between the double well. So there's a delta T and a delta. And now you let that run on a periodic cycle. And then if you avoid closing this, you avoid going here to the center, so you either have a finite delta or a finite delta T, then you will achieve a topological pumping in the following sense. If you look now at an atom, say, being on the double well, localized or mostly localized on a double well, symmetric double well, and now you do your cycle, then you will kind of fill it into the next well adiabatically, and then from the next well into this double well, which is shifted with respect to the first one. And you move that. Now you could say, yeah, okay, it is nice, but why not just take the large wavelengths lattice and shift it? There is one non-trivial point, and the non-trivial point is actually that if you have the short wavelength lattice plus the long wavelength lattice, you will have 2 low energy minibands. The lowest energy miniband will move to the right, while the miniband above will move to the left. And from an experimental point of view, the super nice thing about this system is that there is an energy separation between higher bands and all these low bands. And that means that you can run this system with interactions without heating. In Floquet-driven systems, you usually have the problem, so you drive here, there you drive between those bands, so you get a certain population in the higher bands, but if the atoms interact in the higher bands, they might get stuck in these higher bands. These problems don't appear due to since everything is happening in these 2 lower mini bands. So how do we implement it? The challenge in previous experiments had been that, well, if you take a lattice at 1064 nanometer plus a lattice at 532 nanometer, you can produce a laser light easily. However, each frequency feels a different refractive index in air, and that refractive and that difference actually changes a lot with temperature, with humidity, and so on. So the technical control of taking 2 very different laser frequencies is not unsurmountable, but challenging. In our case, what we actually, from another experiment we did there, we realized that this is a method to do. There we realized we can actually get a laser configuration where we have 2 lattices, one with a large period, one with a smaller period. And if you do not perfectly retroreflect one of the lattices and change one of the frequencies, then you get a situation as illustrated here, where this larger period lattice moves with respect to the shorter period lattice. But these are generated with almost the same laser frequency, right? So just 100 megahertz or so difference. And then you can make it into 1D system by just increasing the intensity or reducing the tunneling on some of the bonds. Then there you see this is exactly the situation you want to have. And this is a configuration illustrating the light field configuration that we use. And sometimes, I mean, all the experimentalists, you probably know that sometimes, well, you do something and at the beginning it seems simple, and then it might take a year after all because all the unforeseen problems. But here it was a really nice, experience. It was just the opposite. So we had the idea and then implemented it, and immediately on the first try, it actually worked. So, and here you can see one of these first results where we put the cloud into this lattice configuration and then switched on the topological pump, and we see here these atoms are transported. Here are also some atoms going the other direction because we filled not only the lowest miniband, but a little bit also in the next higher miniband. And we could then play with the interactions. And one non-trivial thing we observed with the interaction, I will come to that. But the question before that we asked was then, I mean, it worked so well that at some point the atoms would reach the end of the trap, the harmonic potential. And there was not much literature on what is happening if you have a topological pump in a trap. I mean, people either used hard walls, or sometimes you could read the atom stop or something. But what is happening, actually, you have a region where the topological pump works, and then you have, once the side offset and the creation, the gradient due to the trap, when they compensate each other, then you have a transition from a topological region to a non-topological region, and the atoms will turn around. That's for non-interacting. And now one can do that for interacting system. And what one sees there, that you get a second reflection earlier for repulsively interaction, because then the interaction energy can also bridge the gap, and then your kind of the transition to lower to non-trivial topology happens earlier, and you get a reflection of part of the atoms. So these are the atoms transported, and these are those reflected. And there we also realized, okay, so these are pairs, and it will break our pairs, and there will be a correlation between spin up and spin down. That was where we started to think, maybe we can do put a focus on this effect. So now I'm coming back to the singlets. We have the singlets in the potential, and now we can also do a pumping of the total of all these singlets, of the joint pairs. And that, if we do that experimentally, we can see that we get, per cycle, we get fidelities of 99.5% over a large, averaged over a large sample. Now we want to split them, or I showed you earlier how we can split the atoms on a double well. And now the measuring of that, whether that process is really coherent, one uses singlet triplet oscillations. That's applying magnetic field gradient, because that is the only thing that destroys your decoherence-free subspace between singlet and triplet states. So you apply a field gradient, and then singlets and triplets oscillate one state into the other. And then, depending on how long you apply your magnetic field gradient, you will see a periodic oscillation in the singlet in the singlet fraction. Now we combine everything, this producing the singlet, being able to measure the singlets. Well, that was the last part of measuring the singlet triplet oscillations. And now we apply the topological pump. So we take the pairs apart, and now we pump them. And now they are further apart. That means a weak magnetic field gradient will lead to much faster, or the same magnetic field gradient will lead to much faster singlet triplet oscillations. And that is exactly what we saw. Much faster singlet triplet oscillation and with a super high coherence time. So we apply this gradient, system makes singlet triplet oscillations, and then we reverse the pump, bring them back into the same site. And now you might have a little uneasy feeling. And the uneasy feeling might be that, I told you we have these singlet pairs on almost every second site. So what's happening when those pairs we split them? I think I could convince you, but then they might collide into each other. And for that, we use swap gates. So what we do is, if they come together, then we implement a super exchange swap gate and then let them move on. That is how we actually get the very high fraction of the atoms to recombine them in singlets. So we split them, they pass through each other, we do the singlet triplet oscillations, and then they go back. And we can do that for different distances, and up to, I think we did up to 19 lattice sites. And that is kind of an illustration. So these pairs are taken apart, they pass through each other, but the entanglement is still between the original ones when they go back. But we can also, instead of swap gates, we can also have variable swap alpha gates. And those are shown here. And in particular, we can also do swap square gates, which are reflections. And those reflections, here, the particles interact, but the same color goes back on its initial trajectory. So it's reflected. And then, of course, much earlier you will recombine them, and you can see that in your singlet fraction measurement. And that is, these results, we are very happy, of course, about them, because that means now that you can fill your lattice with singlet pairs, with entangled system. And you can now think about connecting distant pairs. And that with a high fidelity. Now in the lab we now have preliminary results that we get the swap gates with 99.8 or 99.9%. So one can then imagine really to let them go through each other and then decide site 1 with site 7 we want to interact with a swap whatever gate, and then create a state, some non-trivial entangled state. And one can also do that in the different directions. In perpendicular directions, it's just more complicated, but should work. Okay, that is this part. And we believe, I mean, it's of course our approach that using the interaction of the atoms in the ground state compared to, say, the advanced techniques of Rydberg interactions, this ground state interaction that will always be the same. They are in their external degree of freedom absolutely controlled, and then if they pass through each other, it will always be the same interaction. There is no precision wiggling and so on. So in principle, we think it is rather scalable, and we can create 50,000 of those pairs easily. Okay, so this is where we stand. There's still a lot to do and challenges. And now I will come to the second part, and that's about quantum simulation of devices. So usually quantum simulation, how our community uses this term, is that you have some Hamiltonian and you implement it in your experiment, and it should reflect, say, some properties of materials. But it is, the interest there is what is a property of the material, of one material under certain conditions. With quantum simulation of devices, one could more think of, but I really want to have a functionality and I want to simulate the whole system. But okay, I show you this electronic circuit, but there you will say, that has nothing to do with quantum physics. So then one has to go back. What are the most simple devices which are truly called or rightly called quantum devices? And one example is quantum point contact, basically where you have two electron gases and then connected by a single channel, and there you will get the results of quantized conductance, and the reason for that lies in the Pauli principle and Heisenberg. So it is, I think rightly one could call it a quantum device. However, these devices, one cannot control the interaction, and usually it's just basically a Fermi gas. Whilst implementing that with cold atoms, one can answer the question, what is happening if you have interactions? The theory for a long time, basically there was, they had, of course, at one point thought about it, and then they came to the conclusion, as long as I have a Fermi liquid, it will always be the same, just you have quasi-particles instead of fermions, so everything should be the same. But, well, that's not so simple. Okay, and this is the team over the years where we worked, and we have also theoretical collaborations and with the thermoelectric transport with Antoine. And you see everyone here. And Jean-Philippe, you will see next week. He was also an instrumental part in these measurements. And that's what the experiment looks like. Really cool colors we have in our lab. And that is the basic idea. So we have this elongated cloud of lithium atoms, so it's fermionic lithium with a very nice Feshbach resonance, and where you have attractive interactions and a robust superfluid. And then we use laser light to shape it into a condition where we have a left reservoir and a right reservoir and a channel. And I will show you how we, at the moment, we are now able to structure the channel almost at will. The idea of the measurements are rather simple, rather textbook-like. So you have two containers, and then you have a hole between the containers, and then you look at them equilibrating. So say if you have more atoms on the one side, and then you wait a time, and then we take a picture, and then we repeat the experiment and so forth, and we can take the picture at different times. And then we can measure the particle transport, we can measure the energy transport and spin transport. But I will focus on the particle transport here. And I mean, the first result that we had was simply an exponential decay of the number, so not a big surprise. But then we, of course, were wondering what is the decay constant, and that is given by the number of channels that you have, by the conductance, and that depends on the number of channels. And then we thought, can we go to the regime of a single channel? And indeed, with our experiments, we could do that, and then we could reproduce what our condensed matter colleagues had done long before. We could see these quantized conductance steps. And since that is a conceptually important part of also then interpreting the experiments, I will briefly remind you why you see this quantized conductance. So you have the left reservoir, the right reservoir, and we now assume that our chemical potential difference, so the different number of atoms will lead to a chemical potential difference, that is small compared to the second transverse level. What do I mean with second transverse level? So you can treat the direction here simply along the channel just as momentum states, but the transverse axis, in the transverse direction, you have to look at your levels in a quantized manner. And let's assume that only the energy of the chemical potential is only high enough that the atoms are conducted in the lowest channel. So we can forget this one higher channel, and we can ask the question, what is the current that is flowing at a given chemical potential difference through this one mode? So optics people would say mode. And you can calculate that taking the density of states of the right moving particles, the velocity at the center, and the transmission, which is almost 100% in our case. And then you see that your current is proportional to the difference in chemical potential divided by h, where h is not just some number, it's Planck constant. And your conductance correspondingly is 1 over h. Each channel gives you a conductance of 1 over h, and that's given by Pauli principle. You cannot fit more particles in, and Heisenberg, it's the wave nature, you have this mode structure. But now what is happening if we increase the interactions? If we have increasingly strong interactions. And this is the Feshbach resonance here. And now let's take fairly weak, but medium weak interactions. And there we still see a conductance of 1 over h. And then we increase, we see a conductance of larger than 1 over h. So there we were already a bit, okay, from our textbooks we expect differently. Then two kind of people say, maybe there are pairs. Then we see a clear shoulder at 3. And if we go close to the resonant case, then we saw super fast conductance and no longer linear. Then we focused on this regime because that regime, the equation of state, is known for the gas, the unitary Fermi gas. I mean, Christoph Salomon did a lot of important experiments on that, the equation of state. And so we controlled now this channel, the chemical potential within the channel with this additional laser beam, like a gate beam you could think of. And there we see that that's delta n over n as a transport time. There you see clear nonlinearity. And so you have a superfluid on the left, superfluid on the right, and then you see this nonlinearity. I mean, our expectation was, of course, we should see Josephson oscillations, but that's not what we saw. But I will come to that. And we got together with Thierry and then looked at, well, they came up with a theory, and the basic theories, I mean from the energy scales, the difference in chemical potential is small compared to the gap, to the breaking energy for the pairs. And the basic idea of their theory is that you transport several pairs and you break one of the pairs. So you can, and that has different also, you have increasingly higher order processes if you want to, at very small chemical potential difference, if you want to have a directed current. So a directed current means you need to dissipate your energy, you need to couple to other states somehow. And you can then imagine that if out of 7 or 8 pairs, if you break one pair in a high order process, then you can have one particle reflected but the other transported. And that also gives you a nonlinear behavior. So there's clearly a nonlinear term in that physics. And then we were wondering, what is that? Is that a mixture between a superfluid? Because obviously it flows much, much faster than we would expect from a Fermi liquid. But on the other hand, it's also not a superfluid because it should show Josephson oscillations. And then we thought, what's happening with the entropy transport? How much entropy is transported? Since all this, as I said, pioneered the work was here by Christophe Salomon with the equation of state. So we are able to measure the equation of state before and after, and then measure how much entropy had been transported. And that was the result. The entropy goes with the particle number. So not very superfluid, but fast transport. Fast transport, but not what you expect from a superfluid. And the entropy per particle transport was around 1 kb. So this means, in a way, that if you go close to superfluid, you can actually accelerate your entropy transport, which might be, thinking of thermoelectric devices, could be very interesting, also for technical reasons. We also looked at pure energy difference, a bit along the lines of thermoelectric devices. And there one can see that one has a very fast response for the particle number, also for the entropy transport, and then you have a nonlinear quasi-steady state. But again, the fast response was 1 kb per particle. And that's unusual for our field. Usually we have these microscopic equations, and then from them we can calculate what gets out, what we see in the experiment. Here it was not possible. There's no microscopic theory as yet, but if you ask theorists, what are the transport properties of a strongly interacting Fermi gas, they of course say, oops, I don't know. And we can describe this with a nonlinear transport equation. So we have to add a nonlinear term, and then we can consistently fit the data. That there is a nonlinear term in it, I think it's not so unexpected, because in the limit of when we have this multiple Andreev reflections in a small channel, there is a nonlinearity in it. So it will not, if we go to higher temperatures, broader channels or whatever, it will not just evaporate into nothing. So I think they make sense that we use these nonlinear equations. And now, most recently, and this is preliminary work, we changed the way how we produce our tunable channels, and we use a digital mirror device to project different structures. And well, if you then measure, that's how it looks like. And then we did also some other optimization. Then we were very happy to see regimes actually with oscillations. So where we see, and that was not in the very narrow channel, it was a bit wider channel. There we saw some very nice oscillations. And then if we go up in temperature, they would damp faster. And overall, our picture at the moment is, at the non-interacting and single channel, or single 1, 2, 3 channels, we have this quantized conductance. If we increase interactions, then the pairing allows more particles to go into the channel, or another way is maybe the channel is almost a superfluid already and allows to grab more particles, more transverse modes out of the reservoirs. Then we have a unitary, we have this kinky nonlinear regime. And if we then go to somewhat wider channels, then we can see Josephson oscillations. If we are cold enough and if we get warmer, they damp faster. And then there is at a certain channel width, then they decay faster. So that's the situation, our understanding at the moment of this quantum point contact with interactions. What next? The pain with these measurements is always to extract the equation of state. You need to know your imaging very well, and so forth. So that is a bit painful. So the thought was, couldn't one just produce masses of these images in masses of different configurations, and then feed these images into an AI, so image and channel type, and then forget about this equation of state. It has all the information, the images, and then feed a big neural network and see whether it can then produce always the right thing that we expect. We are collaborating on that with Johan Karaskila. We have no preliminary results yet, but we like the idea. With this, I would like to thank the teams. I didn't talk about cavities, but it's also interesting, just as interesting. But I would like to thank them all, and it's a great pleasure to work with each of the co-workers. And with this, I would like to thank very much your attention.